Good morning, everyone. Thank you very much for the invitation this morning. I do apologize for the tone of my voice. I actually came down with COVID last week, but thanks to the miracle of modern vaccinations, it was really just like man flu. So getting over it now, but I'm still a bit nasal. Okie dokie. I'm going to get right into this and tell you that when I was a kid, I was a big fan of Wile E. Coyote. He was actually my favorite cartoon character, partly because he was a pioneer, he was an early adopter, but sometimes he just ran out of road. And I think the goal of this presentation is really to ask the question, is optical fiber running out of road? And if it is, are there things we can do about it? Now, the reason that you should care about that is that optical fiber is essentially the oxygen that feeds the internet. The capacity that optical fiber delivers over such great distances cannot be replaced by any other medium. So you might think, oh yeah, 5G will help us. I mean, the thing is, the radio portion of a 5G network is only between the handset and the first cell tower, which is typically a few hundred meters away. The rest of a 5G network is optical fiber. Similar thing can be said for satellite networks. And if any of you have actually used Starlink, you know it's extremely unreliable. It can't replace a fixed line broadband, but it's better than nothing. So let's take a look at that question, and I'll start with some perspective. For those of you who are not familiar with optical networks, this is about the simplest long distance optical network you can get between a couple of points of presence or data centers. So we've got the optical fiber. We also have these buildings along the way, and these are amplifier sites. And these appear in long distance networks every 50 to 100 kilometers. If you've got a really short optical network, you may not need these. So I'm going to divide the network up into these three color-coded areas of transponders, line system, and fiber. And at the ends of the network, in the data centers, let's say, we'll have elements from the line system. The line system is about gathering up wavelengths and combining them onto the fiber. You may also have optical switches called ROADMs that allow you to redirect the flow of light to other directions. We also have transponders, which put the ones and the zeros into the optical fiber here. In the amplifier buildings, not surprisingly, we have optical amplifiers, and there are different technologies I'll explain as to how we use that. Now, the reason I've broken this down in this way is the dial on the right-hand side is telling you that if you decide to upgrade different parts of your network, it will have an implication for investment. So the easiest, the lowest impact will be for the transponders. And this is what service providers like BT do all the time. You track a transponder evolution curve. We're in a type of technology called coherent transmission. We've been there for about 10 years. And in that 10-year period, we've been through 5 generations of coherent transponder. Each generation gets more capable. A little bit more impact is if we upgrade the line systems, and then the highest impact of all is upgrading the fiber. Now, that's a little bit of a bold statement, because if you've got empty ducts and you just want to blow some fiber along those ducts, it might not be that bad. But the idea of upgrading the entire national network of fiber is quite a daunting prospect. So how much capacity is in an optical fiber? Now, I know many of you are sitting there before your first bacon sandwich of the morning. So I want you to brace yourselves, because I'm going to show you an equation. And this is the Shannon equation. It's actually a simplified form of the equation. And this dates back to the 1940s, a guy called Claude Shannon. He was a researcher at Bell Labs. Now, obviously, he wasn't dealing with optical fiber. He was dealing with wireless communication or copper communication. But the basics of what he formulated for information channels is still valid for optical fiber. So on the left-hand side, this is what we're trying to calculate, the theoretical maximum capacity of the fiber. And on the right-hand side, it really just breaks down to 2 terms. The first is the B, or bandwidth term. And what we mean here is how much, and this is in the context of optical fiber, obviously, how much of the fiber spectrum can we use? How much of it are we amplifying? Remember those amplifier sites for the long distance network? We're not amplifying the entire spectrum of the fiber. We're only amplifying a section of it. And in fact, we've gradually amplified more of it over the 25, 30 years or so that WDM has been around. Wavelength division multiplexing has been around. We start with something called the C band. This is where we like to live with optical fiber transmission. The conventional band of wavelengths used to be 4 terahertz wide back in the early days. It grew to 4.8 terahertz and then 6 terahertz. How did it do that? The amplifiers got better. Remember that portion of the network, the sections of the network I showed you, we upgraded the amplifiers within those amplifier sites. We could also double the capacity by lighting up an entirely new band of waves. It's not that new. We've known it's been there for a very long time. But from practical purposes, there are implications in doing this, but you can double the capacity by lighting up the L band, the long wavelength band as well. We could put exotic fiber in, like multi-core fiber or hollow core, and also we could just put more fibers. There's always the option to deploy more fiber, but that costs more. The idea is we want to try and get more capacity out of the existing fiber. So then there's this SNR term, the signal to noise ratio term. The better the signal to noise ratio, the further you can transmit before you have to digitally regenerate the signal, or the faster your wavelength data rate can be. And this is at the receiver, the signal to noise ratio at the receiver. Now, the interesting thing about the SNR term, if any of you here work with wireless technology or copper technology, one strategy to improve the signal to noise ratio at the receiver is to turn up the power at the transmitter. The problem with optical fiber is you can't really do that. Well, you can't do it forever because there is a non-linear limit to signal power. If you turn up the power too much, you end up generating lots of noise, basically. But what we can do is use better fiber, we can use better line systems, and the big one is we can track this transponder evolution curve. And the problem with the transponder evolution challenge is if you look at the everything that is in this green term, this is where the transponder improvement happens. And the problem is it's in a log function. So if we look at this chart here and we look along the horizontal axis, there's a vague concept of capability, improving the capability of the fiber or the transponders or whatever. If we improve the capability of things that influence the bandwidth term, we increase capacity in a linear fashion. Double the capability, you double the capacity. That's fantastic. However, if we double the capability of the transponders, because it's locked inside that log term, we don't double the capacity. So you might say, gosh, maybe we should just focus on the bandwidth term. And today we sometimes refer to that as building more road. It's increasing the amount of road that we've got on the medium. But the point of that network diagram I showed you earlier is so you can consider the scale and impact of the upgrades. Expanding the C-band, all of these things here involve new fiber deployments or new line system upgrades. So they have a lot more impact. Tracking the transponders, that can be done very quickly and easily. It's not service interrupting for the existing transponders that are already using that fiber, and that's what we've done over the course of time. Now, a summary of the options. This is kind of like a roadmap of options. I'm going to be focusing on commercially available solutions. I'd be happy for a future invitation to look at the future technologies, but this is the only way I could keep this down to the time allowed. And in the commercially available solutions, we look at existing fiber, existing line systems, existing fiber, but upgrading the line system, and then the idea of deploying new fiber, perhaps at the same time, upgrading the line system. As we move from left to right, this is increasing the investment. And then in future technologies, I won't be discussing, but there are things like moving to multi-band, multi-core fiber, multi-mode fiber, and hollow core fiber. And I tried to do an equivalent left to right thing here. There's just a couple of columns that are applicable with the idea of risk. In other words, what is the risk of that technology either never being commercially available or it kind of dies out very quickly? And multimode fiber, I think, is definitely a high risk option. Multi-core fiber, on the other hand, is almost certain to happen. So I'm going to fill this out. I'm going to build this out. I'll be talking about these green blobs on the left-hand side. I won't be talking about the blue blobs on the right-hand side. I will mention briefly hollow core fiber. And that's because BT has actually issued some press releases about network services based on hollow core fiber. However, these are not about capacity at the moment. The current generation of hollow core fiber doesn't give us any more capacity. What it does do is allow lower latency transmission. So for the crazy people who are doing algorithmic trading and need to shave off milliseconds and microseconds of latency, and they've also got loads of money, by the way, then they are happy to use this kind of fiber for low latency. So the other factors affecting your decision, and believe me, there will be people within BT who don't just look at these as bullet points. They are poring over surveys and spreadsheets of all of these factors, like how much spare capacity do you have on your busiest routes? And more importantly, how do you decide if they're full? Because you may have a policy that says we don't go over 50% of capacity because we need to be able to back up other routes. Is it how far are you going? Is it metro, regional, long haul? Submarine is a special case, by the way. Do you own dark fiber pairs? Sometimes it's easier to just light up a dark fiber if you've got it. Are you leasing fiber pairs? Because if you are, you just doubled your cost by leasing another fiber pair. Are new fiber pairs even available? What level of demand growth do you expect? And are there factors that are going to trigger a surge in demand? Look what happened last year with COVID. We faced something like a 9% unexpected increase in demand worldwide. That was over and above the normal growth that we expected. And that was because of the redistribution of bandwidth because of COVID. What level of investment risk is acceptable and what's your time frame? All of these things and more have to be considered. So let's take a look at the transponder generations. This has really been where a lot of low-hanging fruit has existed. And I mentioned that we're up to the 5th generation of these transponders. This is the 800 gigabit per second generation. What happens is each of these generations tends to deliver at least a 30 to 40% reduction in your total cost of ownership. For example, by moving to a higher data rate per wavelength, you're able to satisfy a bigger demand for service capacity by buying fewer transponders. Now, that's got to be a good thing. That's costing you less. You're using less electrical power. You're using less rack space. That's part of this TCO reduction. If a generation cannot demonstrate that improvement, you don't deploy it. It's as simple as that. This is not just sort of marketing BS. If we can't justify that TCO reduction, you're not going to bother deploying the new generation. This is the improvement in the C-band capacity, the fiber capacity over that period of time. Now, the interesting thing is the first generation of coherent appeared about 2010, and it replaced direct detect transmission. When it did that, it boosted capacity by a factor of 10. Now, you don't get many factors of 10 improvements happening overnight, but that was one of them. That was an incredible improvement. But since we've been tracking coherent generations, we've got about another factor of 5 improvement. Now, what you can see in the last couple of generations is the evidence that we might be approaching the Shannon limit, as dictated by that equation I showed to you. And let me just tell you, you don't calculate a Shannon limit for the world. Every single fiber pair on the planet has its own Shannon limit. And so, these numbers that I'm quoting here make a number of different assumptions, but this is typically what you would expect. Now, capacity on its own doesn't tell the whole story, particularly for the last few generations of coherent. So those are the numbers that I've just shown you for the third, fourth, and fifth generations. Third generation, that was the 400 gig per wave generation. But if you operated the transponders at 400 gig, you could only go about 120 kilometers before you had to regenerate the signal. That limited the applicability of those transponders at the maximum data rate. What you could do is turn down the data rate and you could go thousands of kilometers. The similar thing happened with the next generation at its maximum data rate, the 600 gig generation. That was about 150 kilometers. But a very interesting thing happened in the latest generation, the 800 gig generation, because of certain advances, particularly a technology called probabilistic constellation shaping. We can achieve a much greater reach at its maximum data rate, and that improves your economics dramatically. So this has been a very fruitful process of tracking that transponder evolution curve. Now, an interesting option, and I don't know if Andrew Lord from BT is on this call, but he took part in a series of discussions at OFC this year, which is a very large conference that focuses on optical technologies, on low margin optical networks. So what is margin? So basically in optical transmission, when you if you transmit from left to right here, errors are introduced in transit through the fiber. And the object for the optical receiver is to deal with those errors. Now, we use something called forward error correction to try to correct errors without having to retransmit data. But if the errors get too great, then unfortunately your forward error correction breaks down. Now, we measure the quality of the signal arriving at the receiver using a factor called Q. I won't go into how it's calculated. It's just a factor. And we have something in each transponder called the FEC threshold, the forward error correction threshold. And if errors, if the quality of the signal arriving in the transponder is below the FEC threshold, you will start to generate post-FEC bit errors. What that means is your customers will start to experience errors. The phone in your network operations center starts ringing. Life gets very exciting. So what happens with service provider networks is you set a service commissioning limit that is well above the FEC threshold. And the difference between these two, broadly speaking, is the margin. It's a safety margin that you're building into the network. Now, there's lots of different sources of margin, and in fact, there's a very interesting paper if you wanted to delve into this. I'm not going to be going through this diagram. You'll be happy to know, but you can see that margins are not only quite complex, but they change during the life of the fiber, and that's because there could be fiber aging, there could be aging of the transponders, and so on. And typical margins today are decided by the network operator. BT will have policies within your design departments that determine these margins. Well, how would you reduce them? Why would you reduce them? Because you've essentially got margin in the network. Because so many people are adding margins, you could justifiably ask the question, do we have too much margin in the network? And how would we monetize it? So what happens if you reduce them? Well, OPEX costs tend to rise because now you're having to respond to errors that your customers are potentially seeing. Customer satisfaction could be impacted. Well, the panel at OFC was really discussing how would you mitigate the consequences of reducing margins? You could identify the most vulnerable routes. And also you could use machine learning and analytics within your transponders to try to predict quality of transmission failures before they get through to the customer. And you can do something about them without impacting your cost of operations too much. But the consensus of that panel said it could be possible to double existing capacity. Now that's particularly true for incumbent operators with very complex national networks where you have to apply blanket policies to the whole thing. By going to a more granular margin strategy, you might be able to increase existing capacity quite significantly. So let me have a look at a few of these line system options here. Back in the old days, when we put lots of different wavelengths onto an optical fiber, this is the basis of wavelength division multiplexing. Each of these wavelengths lives in its own fixed channel. This was a fixed grid system, and it was like lanes on a motorway. So if you look at the old 80 channel 50 gigahertz grid, this works for certain kinds of signal. It works for 32 gigabaud carriers, for example. The baud rate is the rate at which you send optical symbols. It didn't work so well for low baud rate carriers because you were wasting space. You can't have more than one optical signal within a grid space. And for modern high baud rate signals, it was just incompatible because you're not allowed to spill over the edges of the grid. So what happened around about 2013, flexible grid systems were introduced. And what you do there, you don't have a fixed grid. You build a flexible sized grid slot, and you do it on a 12.5 gigahertz granularity. So this is what we tend to use these days. Now, the next thing we can look at is better amplification. Now, I was advised that you're not all optical experts, but just bear with me for a second here. These are types of optical amplifier. EDFAs have been around for a long time, as have Raman amplifiers, by the way. If the signal is propagating from left to right here, if it's transmitting from left to right, we could imagine in the amplifier location, the EDFA gain essentially occurs at point A, whereas the Raman gain, because of the way Raman works, it tends to occur towards point B, just before the next amplifier. And so a great option is actually to combine these two amplification technologies into a hybrid amplifier. And that's, again, that technology has been mainstream for over 10 years. However, Raman amplifiers are more expensive. They may have unwanted operational complexity. The pump lasers for Raman are very powerful. They're quite dangerous. You have to have Raman trained staff. Now, what about lighting up new wave bands? Now, this chart actually shows the attenuation, the amount of energy that's absorbed as a signal passes through glass. You'll see there's if you follow the red plot, there's a big water peak in older optical fiber, and that's because basically the people who manufactured the fiber didn't realize that would be a problem. As soon as they found that out, which is actually quite a long time ago, they started to manufacture fiber in water-free conditions. So you can see there's a dotted line there that removes the water during manufacture. That's a logarithmic plot on the vertical axis, because basically the ideal operating wavelength is the C band. This is why we tend to operate there, because that's at the minimum attenuation. Luckily, L band is also close to that minimum attenuation. And so we can use a combination of amplifiers, optical amplifiers, particularly EDFAs, to boost both the C band and the L band. And because of the way these EDFAs work, you can't do them in series. You have to do them in parallel. So what you end up doing is breaking apart the C band and the L band wavelengths. You amplify each one through its own optical amplifier, and then you put them back together again. And although you can double the capacity, there's a little bit of operational complexity in doing this. You have to build networks that are C+L ready, but the bonus is that you might get twice the capacity. Is there an easier way of doing this? Well, there's a lot of work going on. I mentioned that the C band, we've actually expanded it over time. The traditional C band was 4 terahertz. Nowadays, most people are using a 4.8 terahertz. That's 20% improvement in the C band. You get 20% more capacity on the fiber by doing that. And people are now talking about we could improve it even further. We could go to 6 terahertz, an ultra wide C band. That would be 50% more capacity than the original C band. That's called Super C. And it has exactly the same level of simplicity, and presumably will be as cheap as regular EDFAs. So you've got some significant benefits here. And by the way, we can apply the same logic to the L band. We can build EDFAs that operate on a wider range of wavelengths in the L band, and we could build a Super L equivalent. Now, oh, well, actually, let me just go back one. I'm going to be talking about new kinds of fiber, but I'll mention something called ZB-LAN fiber. And the reason I've got a little satellite thing there is that ZB-LAN is this amazing fiber. It's made from different materials. It's not made from silica. It's made from exotic rare earth elements, but it has amazing low loss over a very wide range of wavelengths. The drawback is it has to be made in zero gravity. And so you can imagine that ZB-LAN will be extremely expensive. The industry is planning to make it, but it's going to be for very specialized applications. I can't really envisage a day soon when we're going to have a transatlantic optical cable made from ZB-LAN, because 6,500 kilometers of ZB-LAN is going to be quite dear. But what are the new sensible fibers that we could look at? Well, the original single mode fiber that people deployed back in the 1980s is called G652, and remarkably, it's one of the best fibers you can use for coherent transmission today. There is a new variant of it, G652D, which has a reduced attenuation. It means that you don't have to have amplifiers as often, or you get better Q values basically by using it. And with this kind of fiber, with a modern 800 gig generation transponder, we've shown that we can actually achieve about 970 kilometers of transmission without regeneration at 800 gigabits per second. There is an even better fiber, G654, and that uses a larger effective area of the fiber, from 80 square microns up to 125 square microns for the terrestrial version. There are subsea variants of this fiber that go up as far as 140 square microns effective area. You can't just keep on doing that, by the way, because if you keep on increasing the effective area of the fiber, at some point it stops behaving as a single mode fiber, and you don't want that. But these fibers are an interesting option. There is a little bit of a caveat. Because of the larger effective area, Raman amplifiers don't work as efficiently with these fibers. So there are pros and cons. But we actually did a joint demonstration with Corning, who are manufacturers of fiber like this, their TXF fiber, where we achieved 1,600 kilometers unregenerated reach at 800 gigabits per second. So that's a really amazing performance. There's an entirely different set of fibers, G657, reduced cladding diameter fibers. The cladding of the fiber is the outer layer of the fiber. Now, they're not intended to have a lead in low attenuation or that kind of optical performance, but they're just thinner. It means you can actually fit more of them into a duct. So for metro and access type applications, these could be very interesting, because a 20% reduction in the cladding diameter means you can get 50% more fiber pairs into your duct. So just to sum up, really, remember, I've been focusing on the commercially available solutions. How much capacity is left? Well, I'm sorry, it depends where you are now, because I've covered all of these different green blobs, but you may have implemented some of these options already. So how much more capacity really depends on where you are along that journey. So for example, the transponder upgrades, we've shown that even in the generations of coherent, we've been able to multiply capacity by a factor of five. Low margin networks, if you have a lot of margin in the network, and if you can deal with the consequences of reducing the margins, you could have double the capacity in your network already. Flexible grid, not so much an increase directly of capacity, it's more of an enabler. And it's an enabler for things like high baud rate transmission. Now, Raman amplification, I don't know, 10 to 20%. If anybody knows a better number than that, by the way, let me know. C+L is doubling the capacity. Super C and Super L, again, up to 50% more than just doing like regular 4 terahertz C and a 4 terahertz L. And then large area fibers, again, it's more about increased reach rather than increased capacity, but the two are linked. So I'm going to say maybe up to 20% improvement. So the other gotcha is that these gains are not necessarily independent of each other. So it is a very complex topic. There is still mileage left. I think Wile E. Coyote hasn't run out of road just yet. And again, we have all of these different options. We have a whole set of future technologies that potentially are going to ride to the rescue, including using existing fibers and lighting up other wavebands, which I think is a very mixed picture because of the complexity of the amplifiers, but it's certainly a strategy that could bear fruit. So I hope that's been interesting, and I'm happy to answer any questions.